Welcome back to our lecture, Blockchain-Based Systems Engineering. We have today the very last lecture, and tomorrow there will be the preparation for the exam with Uli, where you can ask remaining questions and get some insights about the exam, which is also an important topic for you. But today it's my pleasure to welcome Dr. Alexander Esslinger. He's actually, the first contact I had with him is on Twitter. And you know, on Twitter, you have people like Trump and all kind of rubbish. But I think he had very nice comments on blockchain-based and other topics regarding our society, etc. So therefore, I got interested, and then when we founded the blockchain-based, the Blockchain Bavaria Association, more or less we got in contact, and he's now also a member of Blockchain Bavaria, and he's a patent attorney at Betten & Reich, and his I think job is not blockchain-based systems, but it's he's a physicist by education, a doctor in physics, and he's in semiconductor technology. So that's more or less the job. But I think his passion a little bit is also zero knowledge proofs, because I think it's a very interesting technology, I have to say, because it does things which sound initially counterintuitive, and therefore I'm very happy that he is the expert, and I looked at his slides to also describe this topic in a way which makes it accessible, because the details are rather complicated, but I think he can make this bridge. Why is this relevant for blockchain-based decentralized systems? So without any further explanations, I'm very curious also to learn a lot today. Alexander, please start your presentation.
Thank you very much for the kind introduction. Let's try to make this zero knowledge proofs a little bit more intuitive. That's the purpose of this lecture, of this presentations. Let's start with a quick overview and outline of the presentation. We start with an introductory chapter, the definition, an example of zero knowledge proof, which is already known. And then it's, of course, important, the motivation. Why are these zero knowledge proofs and these related proof systems important in the blockchain content? Then the main topic, how do they really work? What's the math behind it? And how do they work in some detail at least, and how do they help for scaling of blockchains and improving the blockchain systems? And of course, there are always some trade-offs themselves between different proof systems. In the third chapter, we will try to explain some applications for privacy, scalability, and also business applications. If there is time, we can touch some related topics, which are also interesting, like verifiable delay functions, multi-party computations, or stateless blockchains. So let's start with the definitions. Zero knowledge proofs are a particular type of cryptographic systems. I think at the beginning of this lecture series, you have already learned of some cryptographic systems like hash functions, cryptographic hash functions, or cryptographic signatures. But these zero knowledge proofs are a bit more complex cryptographic systems and also more powerful cryptographic systems. The definition is relatively straightforward. A zero knowledge proof is a method by which one party, the prover, can prove to another party, this is called the verifier, that the prover knows a value X without conveying any further information apart from the fact that they know the value X. So in particular, what the value X is not disclosed to the proving party, to the prover. So the essence of zero-knowledge proofs is that it is trivial to prove that one possesses the knowledge of a certain information by simply revealing it, that the prover shows X, or the witness. The challenge is to prove such possession without revealing the information itself or any additional information. One example is already quite well known to you. So this is digital signatures based on asymmetric cryptography, like, for example, elliptic curve cryptography. These are special examples of zero-knowledge proofs. The person holding the private key can convince any holder of the public key of his or her knowledge of the private key without revealing the private key itself. Of course, otherwise it would no longer be the private key if you have to reveal it, but you can show you are in possession of the private key. So the whole cryptographic system, the whole blockchain world is somehow based on a zero-knowledge proof. Otherwise, it would not work. But as you have learned in the cryptographic basic lecture, these digital signatures can only sign very small amounts of data. And these zero-knowledge proofs, or more generally, it's their generalization, called probabilistically checkable proofs, or PCPs. We will talk quite a lot of these in the next slides, can verify arbitrary amounts of data, or in practice very large amounts of data, and are therefore much more powerful cryptographic tools as these well-known cryptographic signatures. So zero-knowledge proofs, what are the properties we speak of? They are completeness, soundness, and the zero-knowledge. Completeness is a statement is true if an honest prover can convince an honest verifier. So, and this is in typical zero-knowledge proofs is 100% true always. So if the prover has the knowledge of X, the proof allows with 100% certainty to convince the verifier that the prover has the knowledge of X. Soundness is now the other way around. If the prover is dishonest, so if the prover likes to cheat, the prover cannot fool the verifier. So it's not possible for the prover to cheat the verifier. This soundness is not 100%. This is probabilistic, but it can be made the soundness error can be made very small, something like 10 to the minus 20 or 10 to the minus 40. The third property is the zero knowledge. That's the name, where the name comes from. So no information is revealed to the verifier, or more general, very little information is revealed to the verifier. So asymptotically few information is revealed. So the motivation, why are zero knowledge proofs now used for blockchains? And this is because zero knowledge proofs and these probabilistically checkable proofs can help solving two major problems occurring in blockchain networks. The one is the well-known blockchain trilemma between scalability, security, and decentralization. So it's very difficult to achieve all these three at once, as you are well aware. But scalability is necessary for mass adoption of such blockchain systems and also of business style adoption. So if big business want to interact using blockchains, a certain throughput has to be is necessary, has to be guaranteed. Otherwise, the blockchain is not useful and not suitable for business applications. The second dilemma is a so-called privacy dilemma. Of course, in blockchains, we want to have a transparency that differs it from previous systems, but we also need privacy, in particular with respect to data protection laws, or also for business applications. Again, if companies cooperate on the blockchain, it must be ensured that sensitive business and trade information is not revealed to, for example, competitors. Otherwise, nobody would engage in a blockchain-based cooperation. Therefore, the solution of the privacy dilemma is also very important. And here, the zero-knowledge proof can help as well. So to summarize a bit the trust model, we have the traditional trust model, which we want to overcome by a blockchain system. We trust in a particular person or organization of authority. For example, a person of authority hereby verifies that account XYZ at bank ABC holds euro, let's say 1.9 billion per a particular date, and you have simply to trust. In the blockchain world, it's different. The blockchain trust model says don't trust, verify. So we have a distributed, inclusive accountability. The truth of it is verified in every blockchain node. So everybody who wants to participate in the verification can do so. And the blockchain trust model is based on both cryptography and game theoretical incentives. As you have learned in the previous session, for example, the mining procedure is such a game theoretical incentive to ensure that the verification is performed properly and is accessible to everyone, is no closed shop. And zero-knowledge proofs now shift some of the burden away from these game theoretical systems to cryptography to make these game theoretical systems more lightweight and therefore improve scalability. I make a short break here and ask are there some questions? If not, I just continue with a short historic overview, and then we go into the technology. Okay, let's go on. The history of zero knowledge proofs it goes back already quite far. The seminal paper was published in 1985, titled The Knowledge Complexity of Interactive Proof Systems by Goldwasser, Michele Rakoff, and they got the Turing Award, the prestigious Turing Award, quite some time later in 2012. In 1992, there was the more generalized PCP theory was proven, and these more general probabilistic checkable proof systems were introduced by many authors who contributed to these. Already in May 2013, it was proposed at a Bitcoin conference to use zero-knowledge proofs for Bitcoin. And in October 2016, the privacy coin, the privacy cryptocurrency Zcash, based on such zero-knowledge proofs, was introduced and went live and is still working. And in the last 1.5 years, 2019-20, there was this so-called Cambrian explosion of new zero-knowledge proof systems. They suddenly became very popular. lots of systems with different trade-offs appeared and were also practically applied as scaling solutions, in particular for the Ethereum blockchain. So how do they really work, and what's the mathematics behind it? As already said, it's the PCP theorem from 1992, and in a very formal formulation, it can be explained as follows. Every decision problem, so a true-false problem in the NP complexity class, has probabilistic checkable proofs of constant query complexity and logarithmic randomness complexity. If we want to express this a bit more intuitive, it can be said on an intuitive level, the PCP theorem says that there exists probabilistic verifier for proofs of mathematical assertions, so arbitrary mathematical computations, calculations, whatever, which can look only at a constant number of bit positions at the proof, and yet with some positive probability catch any mistake made in a fallacious argument. This means we can take any mathematical computation and check whether this computation is correct or not. Traditionally, you have to do it by simply carrying out the calculation. If you, for example, have a lot of additions to do, you add the values, for example, in a table, you add the values and just calculate and check at every step if this calculation has been performed correctly. And now this PCP theorem says I can make a probabilistic proof of such calculations. And however large this computation is, so I can have gigabytes or more of computation, I can check with 3 bits. I have to verify 3 bits of a proof derived from this calculation, and can say with a probability of 50% whether or not the calculation is correct or not. That's this quantitatively formula which I have indicated here in red color. For an error probability of 2 to the minus k, 3k bit positions have to be verified. And this 3k bit positions is not 3 kilobit, but it's actually 3 times the exponent. So for a probability of 50% of an arbitrarily large computation or mathematical assertion, it's sufficient to check 3 bits. And of course, I can scale this now. If I do not want to have a probability of 50%, I want to, for example, a soundness error probability of 2 to the minus 40, which is about 10 to the minus 12, so 1 over 1 trillion. This is, I think, a very good probability and a very low error. It's still sufficient to check 120 bits of this proof derived from the calculation to check the veracity, the correctness of this calculation. So, and this amazing result, the mathematicians were surprised themselves by this result. It gives a completely different approach to checking the correctness of some computation, including, for example, correctness of cryptographic signatures. Here, the probabilistic approach develops enormous power, an enormously powerful tool for proving such calculations. And these application of these PCP theorem are computational integrity proofs. That's exactly what we are talking about. These are probabilistic proof systems based on the PCP theorem, allowing a prover to convince a verifier of the correctness of an arbitrary computation with the efficiency that is exponentially faster than naive checking of the computation. The properties are completeness, as before. You've seen with the zero-knowledge proofs, a statement is true if an honest prover can convince an honest verifier. The soundness, it's not possible to cheat, or the soundness error or the cheating possibility is very low, for example, as low as 10 to the minus 12. The succinctness is the exponentially faster verification. And we have the zero knowledge, so to say, as a bonus, because we only have to reveal some random bits from the large computation, that no information actually about the computation itself has to be revealed to the verifier. Therefore, these proof systems are generally called zero-knowledge proofs, but the important thing is the probabilistic proof and the efficient probabilistic proof. Are there any questions? Short break at this point? Okay. Then how can we do this? How can we take advantage of this enormously powerful tool of these probabilistically checkable proofs? And these work with so-called expansion codes or error correcting codes. So a transcript of the original computation expanded into such proof using an error correcting code, like, for example, Reed-Solomon code or polynomial commitment, or also a fast Fourier transformation, which spreads the errors within the proof. Interestingly, this error correction function used for these proofs are the same error correcting functions which are also, for example, employed for improving the speech quality or the data transmission quality in a mobile communication. These are the same codes as, for example, the Reed-Solomon code. And then a low number, for example, 3 of statistical queries by the verifier are sufficient to prove the correctness of the computation with high probability. I show this schematically here in this illustration. So we have on the left side a so-called execution trace of the calculation, and we have indicated in red color 2 errors in the calculation. And then we use this expansion code or error correcting code to expand and to disperse the error within the whole proof system. So the execution trace is expanded to generate this proof, but in particular, the error is dispersed among the whole proof system. And therefore, as shown on the right-hand side, any random point query gets a much higher probability of catching an error. So because the error is dispersed throughout the whole proof, if I make some random queries, we have a much larger probability to catching this error. I've given here a simple example, a linear example of how this could work based on an Excel table and a simple summation to check whether or not this summation is correct. A summation like in a restaurant or at a bank or whatever application. So if we look at the table on the left-hand side, we have simply a summation starting with 0, then we have first value, 75, then we have the first interim result, 75, of course, then we add 22, we have in blue always the interim results, and we add the next value and the next value and so on. And at the end, after 20 addition operations, we have the summation value of 1027. And now we want to check whether or not this calculation is correct. How can we do it? Traditionally, we just check every single computation as shown in this little box on the left side. We check whether value C is the sum of the values A and B. And we have to check this value for every position, and then at some point we will find the error. Now we would like to improve the probability to finding this error. On the right-hand side, I have actually introduced a small error here in the box on the leftmost column of the table on the right side. So as you can easily see, I have the interim value 281, then I add 28, but the result is wrong. It's 310, should be 309. I have simply, in the Excel table, added a +1, and therefore we have an erroneous result. To catch this error, the traditional way we have to check, as said, any addition to find the error. What we do now is we shuffle around these additions, these addition operations within the column. So as you can see on the right-hand side, but the same is done on the left-hand part, the positions of the values are shifted from the leftmost column to the next column to the right, is shifted downwards by 5 positions. Then there's made a mirroring operation, so the lowest value gets the upper position and vice versa. Then it's shifted upwards by 5 positions, and again a mirroring operation is made. But what these operations are is not important. Important is only that simply the order of the values has been changed. More elegantly, I could have done it by just applying a random order and shuffling these values around. But what you can see is by looking at these small boxes, the error now appears at different positions of these addition columns. And if I apply at the end a summation, a horizontal summation, so I add up all the values, then I get a summation a column at the right-hand side. And here we see the error, which is dispersed, shows up in many more of these calculations. In particular, we have at the right-hand side now 5 erroneous triples, so to say. So if we check now randomly these single summation values on the right-hand side, the probability to catch an error is much larger. While still, if everything is correct, if we now turn back to the left-hand side, still everything is correct. We have, so to say, on the left-hand side, the correctness assumption. So if the calculation is performed correct, then we get for every check on the right-hand side, on the rightmost column, A plus B will always be C, but on the right-hand table, the error is dispersed and the probability to catch the error will increase with every shuffling step we have performed beforehand. Of course, in real life, with these zero-knowledge proofs, we have more complex operations than additions and shuffling around, but here it shows the principle how these errors can be dispersed among the whole proof system, and therefore we have a good chance of probabilistically checking the error. Any questions so far?
Yeah, so I think we have some questions. Let's start with the first one. Could you please repeat the idea of shuffling positions of the additions in the table shortly with using your mouse pointer? I think we cannot see your mouse. You should. I think you have to.
Okay. Yes. That makes it much easier. Of course. Thank you. Here, do you see the mouse?
Yeah, maybe you can use the laser pointer. If you go on the left lower, there should be some kind of the slides. Should be some kind of functionality to create a mouse laser pointer. Yeah, I think that one.
Here. Yeah, here. Okay.
Yeah, very good. Awesome.
Very good. Okay. This is we have here the whole additions, and here we have the end result. If we want to check the correctness of additions, we look at each of this box with the interim result. So we have, for example, this interim result at 281. We add 28 to it, then we have 309, and we see it's correct. So if we want to check the correctness of the whole calculation, we have to check every box. And when we look at the right-hand side, we see here is an error, and then we can see this is not correct. The result should be 309, but it's 310 because I introduced here this error. Then we can see here we have an error. But we have to check every single intermediate result. So then we have this shuffling around. We have taken this left column, then to go to the right column, what is done, simply I have moved the positions downward by 5 positions. So here the 75 appears here, the 22 appears here, and this box with the error appears now here. Then the next step, starting from the second column, to this column, I have performed a mirror operation. So this position, the lowest position here appears here, the 99 appears here, and the 11 here at the top appears at the bottom. Then the next one, I've shifted upwards again. Here, the 11 appears here, and this 28 with the arrow appears here. And then again, a mirroring is performed. So the 28 appears here, and the 99 appears here. And this is this shuffling around. So we have the same values, just at different positions. And at the end, we make a summation. So we have the 75 plus 11 plus 25 and so on. We have the horizontal sum here at the end. And here, because the sum is horizontal, if here in any of these positions an error occurs at the right-hand position, we will see the error. And we have now in total 1, 2, 3, 4, 5 errors. So in the summation at the right-hand column, we have all these 5 positions having an error of 1, because the total error is, of course, 5, if we compare the correct calculation with the edit calculation with the error. But this error is dispersed among many positions. So if I want to catch the error by making random checks of these boxes, so is C equals A plus B, the probability to catch the error is much larger than if you check here on the left-hand side. So therefore it shows we disperse the error among the positions in order to increase the probability to detect the error.
Yeah, very good. Thank you so much. And I have a further question, which is a little bit earlier. So a student asks, to summarize the PCP, it enables us to prove a possession of a certain number by disclosing only parts of it, but false positives cannot be avoided?
False positives should not appear. So, yeah, let's say the false positives would be the soundness error. So if a calculation is not correct, but will be proven correct, so the verifier finds it's correct, so positive, but in actually it is not. This is, so to say, the soundness error. Yeah, for false positives are the soundness error, and this soundness error can be made arbitrarily low. So in the original PCP theorem, we have 2 to the minus k. So at least if k is 1, we have this false positive or soundness error at 50%, which is very high, of course. But if we increase the k, for example, to the value of 40, we have a soundness error of only 10 to the minus 12, which would be the probability of false positives occurring.
And this 10 to the power of minus 12 is so low that it's practically not really relevant for us to assume that it will fail.
Yes, and you can make it even lower. So in practice, we have 2 to the minus 80 that translates into 10 to the minus 24. So we get really in cryptographic orders of magnitude, which are also used by hash functions, so that the error is so low that it's practically not relevant anymore. You can even easily go to 10 to the minus 40 or something like that. Then we have something like 300 bit here we have to check, which is still an extremely low number.
Okay, so it would be comparable to hash collisions, for example. So that could be...
Yes.
Yeah, okay.
Mm-hmm.
Okay, further questions here. Is the new computation of every step for the error dispersion not more costly than just checking every step?
Yeah, that's an interesting, very good question indeed. This is very costly. You have guessed it correctly. But the point is, which we'll discuss shortly, that this has been done only once. So we can provide and calculate this proof once and then use it more often. And this calculation can be done in blockchain context off-chain, whereas the verification has to be done on-chain and by every node of the blockchain. And the hardware requirements of the nodes have to be quite limited in order to ensure that it's accessible to everyone and that we have a good decentralization of the system. Very good question.
Very good. So questions are piling up a little bit. Let's continue there.
Okay, very good. Yeah.
The false positive concept should persist depending on the number of bits we allocate for verification in the example given. So less bits require or result in a higher probability. False negatives, however, should not be possible. Am I correct in my understanding?
This is exactly a correct understanding. The false negatives are here called the completeness. So if the calculation is correct, the proof will always render a correct result.
So one question, the position check we mentioned would correspond to how many columns we have checked in the addition table?
Here in the addition table, we could calculate the probabilities. If we have, for example, performed 3 checks and we have for each a probability of 1/4, I've not done the calculations, but in principle is also it improves about a factor of 4 by these performing these 4 shuffling steps.
Okay. And next question. Doesn't the size of the data being verified play a part on the number of bits that have to be verified?
The size of the proofs of the data is important, and we will discuss this with respect to the different proof systems. So typically the size is astonishingly not so large. So we have typically systems that having several hundred bytes or up to 100 kilobytes. So the size of the proof is astonishingly small, but contains the whole information which is important for checking the correctness of the calculation.
Okay, very good. I think there are no further questions on TweetBack so far, so I think we can continue. Thank you.
Okay, then let's go on. The example was very easy, but as you have guessed, and I see from the question, the proof generation in practice is not so easy. So here on the left side, I have a copy from a publication of Vitalik Buterin on the topic. It starts by the computation, then we generate an algebraic circuit, and then a so-called R1CS system, rank 1 constraint system, then a thing called quadratic arithmetic program. Then we have the linear PCP, so the probabilistic checker proof. Then we generate of this an interactive proof, which we will discuss shortly. Simply, it's this interplay between prover and verifier. And then from this interactive proof, we generate a non-interactive proof, which is called CK-SNARK. Probably you've heard already of this name, which is used often in the blockchain context. And the difficult part is really to generate these proof systems with reasonable resources for real-world applications. The scientists originally working on the PCP theorem, the mathematicians, they did not expect practical application of these proofs because the generation of these proofs would take thousands of years of computation for large problems where it really makes sense. But they were really surprised in the last years that there are actually real-world applications and practical applications. But this was due to the extreme progress made by the researchers and the engineers finding mathematical tricks to make these steps more tractable, to parallelize some steps or to find some shortcuts to make it more efficient and shorter and smaller. So this is the really difficult part, to make these astonishing results of the PCP theorem applicable to the real world. So we have just heard of these snarks. What I just want to explain the wording briefly. It's called a succinct non-interactive argument of knowledge. So argument of knowledge simply is another expression of such proof systems. Non-interactive is what we will discuss on the next two slides. So we have no longer this interaction between prover and verifier. We do it once, and then in the blockchain nodes, the verification step can be done without the presence of the prover. And then succinct means simply that it can be made efficiently. And then Starks have come up, which are basically the same, but they are in addition transparent. They do not require what we will see later, a so-called trusted setup in order to achieve the non-interactive argument, but these are transparent because they have transparent randomness, as we will see shortly. So now we have replaced these interactive proofs, which are not practicable for in the blockchain context, because we do not have the prover and the verifier at the same time. We want to make this investment in the proof calculation once, and then the verifier can easily perform the verification step, the short verification step at any time he or she wishes. So what we have in the interactive proof, we have the proof, then the verifier picks a location to check whether or not it is correct. Then the second part of the proof, or the same proof again, the verifier checks a second position and a third position. This is unpractical. Therefore, we can use something called the Fiat-Shamir heuristic, and there the interactive dialogue between prover and verifier is replaced by randomness. So the proof already has these positions where we can check. But, of course, the important thing is that prover should not influence where the positions are, because otherwise the prover could cheat. He could designate some query positions, but hide the error somewhere here. So, for example, a double spend in a blockchain. Therefore, these query locations are predefined by randomness, which cannot be influenced by the prover. So we need an external source of randomness, and this is done in blockchain, in zero-knowledge proofs, by a so-called trusted setup. Maybe I make a short break here, whether this non-interactive, interactive proof are there any questions? Okay, so then we go to the trusted setups. So these CK snarks are not transparent. They require a so-called trusted setup to secure the randomness of the parameters determining the selection of queries in the verification procedure. The randomness parameters are generated, for example, using a hash function. The knowledge of the original values fed into the hash function, this is called toxic waste, however, has to be kept secret. Otherwise, it would be possible to retrieve the random parameters and manipulate the selection of the verification queries. And a trusted setup to avoid this is a multi-party computation, which is also so-called ceremony, where these parties together recursively generate random parameters. So we have a hash value, for example, pass it on to the next party. The next party generates some randomness, and it's designed so that if at least one party is honest and forgets its input values, then the randomness of the trusted setup is safe. So we have some shielded external randomness, which then can be applied by the prover, which cannot be influenced by the prover in order to cheat. Then there's something like universal trusted setups, so that these trusted setups can be used for different applications, but originally these trusted setups were only for a specific application, and for every system update, this ceremony had to be performed again. So the ceremony, for example, for the original Zcash chain has become quite well known, because there were 3 dozens of computer science. They participated and randomly bought computers in shops and later destroyed the hard drives. And so that was also a community building effort. But today we have either these universal trusted setups where some secret randomness can be used more often, or we have in these transparent systems where the randomness is for example, derived from the blockchain itself, for example, the last block hash or something like that, some arbitrary precision thereof, which also cannot be influenced by the prover. The next step is, the blockchain scaling. How can I now use these powerful tools of the PCP proofs to improve scaling of blockchains? So the computational cost of independent verification of every single transaction by a large number of distributed nodes having to have limited resources is a main bottleneck for the number of transactions a blockchain can perform in a given interval. So zero-knowledge proofs or computational integrity proofs can solve this problem by generating a single probabilistic proof allowing the verification of thousands of transactions in one step, instead of verifying the correctness each separately. So we have simply something like a batch verification. We put together some transactions or state changes. For example, in the Ethereum blockchains, where I have state updates from one Merkle root to the next Merkle root, and I put several thousand of these in one roll up. So that was called, and produce the proof, and then put the proof into the block, which can be verified much more easily or more faster, in particular, than all the transactions or state updates separately. So as the computational cost of verification grows only logarithmically or less, or even is nearly constant, with the number of transactions per proof, the verification cost per transaction is reduced dramatically. As we will see later in the applications, it can be reduced by 2 orders of magnitude or more. As you have said in the questions, the computational cost of proof generations is very high, of course, but this can be expanded off-chain, so where it's abundant, and it has to be expanded only once. So we generate this CK rollup, this best batch proof for several thousand transactions once off-chain, where we have lots of resources, and then put the proof on-chain for verification. In a recent publication, this was also shown how this blockchain scaling works. Again, we have here the computational cost dependent on the network throughput for a traditional system. So this increases linearly with the network throughput. And now if we use zero-knowledge proofs in the form of ZK rollups, we increase somehow the prover, the upfront costs for proof generation. This increases by a constant factor. But on the other hand, the verification grows only logarithmically with the network throughput. And if we have this line, for example, as the computational a maximum load of the blockchain nodes has this limit, and the verification computational cost grows only very slowly. Therefore, the network throughput can be improved enormously. So we have different properties of different proof systems. So we have trade-offs, like in blockchains itself, we have some trade-offs with the zero-knowledge proofs. We have also trade-offs between different properties of these blockchain systems. With all systems, we have the property of non-interactivity, so we have not the dialogue prover a verifier. Then, as just explained, we have some are transparent, some require this trusted setup to generate this secret randomness, and some have universal trusted setup. Some even are recursive, so we can generate proofs of proofs of proofs, which may be quite efficient for some systems. Then we have these parameters: verification time, prover time, and proof size. These are the three most important parameters. And this is in blue. It is given how these behave theoretically, and in red there are some real-world values given of systems which actually run. So the verification time is between constant and polylogarithmic with n. So n is a measure of the complexity of the computation, and the values are between 2 milliseconds, which is very short, and about 250 milliseconds. The prover time, so to generate the proof, this is in the best of worlds, it is constant with the complexity of the computation, or it's n log n, so it's a factor a bit more than linear. So we have values depending on the complexity, of course, between 1 second or about 100 seconds. And the proof sizes can be surprisingly small. They are logarithmic with the complexity, so they still can be kept quite small. So some are only 200 bytes, and the largest which are used are about 250 kilobytes. So yes, quite small proof sizes which have to be sent around on the blockchain. And another thing is, as in cryptography, are the systems possibly or plausibly secure against attacks of quantum computers? Some are, as you will see, and some are probably not. So here we see real world. This is a very recent publication, how these systems behave. Here we have prover time. Argument size is the the size of the proof and the verifier time. Here we have the number of constraints. This is a measure of the complexity. Constraints are of these circuits, which we have seen for. So they start, for example, here by 2 to the 10. These are 1,000 constraints and up to 1 million in each of these tables. And we have here different proof types. They have fancy names like Fractal, Aurora, Marlin, and Groth 16. Groth 16 is a classic already. This was published in 2016, which was used for the ZK, for the Zcash blockchain, and also many other applications. And these other systems, Fractals, Aurora, Marlin, are only a few months old. Here we can see the prover time starts at about 0.1 seconds and goes up. For some systems, here we have 100 seconds, maybe 300 seconds, and it already gets somewhat impractical. Here we have the argument size, the proof size. Here we have 100 kilobits, so these are relatively large, but we see the Groth 16 and Marlin, they are too small to even be shown, so they have argument sizes in the order of 200 kilobytes, as we explained beforehand. And here we have the verifier time, and here we see the PCP theorem in action, actually, because here for Groth 16, Marlin, and Fractal, the verifier time is actually constant, independent of the number of constraints, so independent of the complexity of the systems. And only this Aurora system goes up. Here is linearly. So this Aurora, therefore, no longer is a snark. It's no longer succinct, but has an increasing verifier time, but probably Aurora has other properties which make it useful for some applications as well. But yeah, these very low verifier times, this between 2 milliseconds and here we have 100 milliseconds, are really 10 milliseconds is really astonishing. Any questions at this point?
Yeah, we have some questions.
Very good.
Let's start from the bottom. I think these also target some topics beforehand, so I think we just go through them. Wouldn't it be sufficient for the verifier to select the positions to query rather than having them predefined? So I think it's about some slides earlier.
I see. This is the move from interactive to non-interactive proofs. So that the verifier just selects a position instead of relying on these pre-calculated positions. Yeah, that's a good question. Probably, I'm not 100% sure, but probably these proofs are very compressed in the end to have these small argument sizes, that it would be very complex to select a particular proof positions, that it would be computationally unpractical. I agree theoretically it could work like this, but in practice that it's not efficient if you have to choose the location within the verification process in a blockchain node.
Okay. Our next question, in slide 16, why is it necessary to use external randomness? What is the problem if the prover decides about the order of the transactions?
The prover can decide about the order of transaction, but not of the location of the queries. These have to be random. Otherwise, the prover could determine the location of the queries and hide the error somewhere where nobody has a chance to a query later, and, for example, hide a double spend attack or something like that. So the whole system of the PCP only works with real randomness. The prover should not have access to the position of the queries. Of course, he can shuffle around the transactions and the calculations, but not the positions of the queries.
Okay, thanks. Next question. Why does the proof generation computation only is executed once and can be reused? So where can we reuse it after we calculate it once?
The proof generation could only be reused if we have the same transactions as input. If we have different input, or for example, different blockchain states, then we have to do this proof calculation at once. There are some systems where you can do an update. So you not have to calculate it from the start again, but you add some transaction or state changes and then update your proof. But you, of course, have to include new transactions in proof generation, yes.
Okay. About slide 21, what are the constraints mentioned in the graphics?
These are, let's go back where we have the constraints. These are this rank 1 constraint system. So we construct an algebraic circuit of the original computation. So the computation is set up as a Boolean circuit where each operation is represented by a particular gate. And these gates, can have a million, or this circuit can have a million gates, and each gate represents this or NOR gates, and it represents a particular constraint. That's meant by this.
Okay. And the last question is growth 16 seems to be the best. Marlin was, as you stated, recently developed. So what is the advantage of Marlin? The growth 16 is still the best here in prover time. Here it's in all, it seems the best. One is it is not, it needs this trusted setup. And it's not a universal trusted setup, but by every update of the system, you have to re-perform this trusted setup ceremony. And therefore, every system update includes some bug probability, so some attack vectors, so to say. Therefore, the growth 16 is a bit, is still used for many applications because it's the most efficient still, but has problems with this trusted setup, and therefore other teams try hard to provide proof systems which are nearly as efficient as the growth 16, but don't have these problems with the trusted setup. Okay. Very good. There are no further questions on Tweetback so far. I think we can continue.
Let's go on. So cryptographic primitives on which these proof systems are based. One actually are based on collision-resistant hash functions and therefore also inherit their properties. For example, these are plausibly quantum secure. So even with quantum computers, you cannot break them, possibly. These, for example, are stars, fractals, or auroras. And also these do not require these trusted setups. Then some use elliptic curve cryptography, which you have already heard of also in these introductory lectures. Some are based on knowledge of exponent or pairing groups. For example, here this cross-16, Sonic, Marling, or one which is quite new, it's called Plonk. Groups of unknown order. It's another cryptographic primitive. These are called supersonic. And these are still under development, is so-called lattice-based cryptography. And researchers work on these because it's also plausibly quantum secure, similar as the collision-resistant test functions, but there are not yet any working proof systems published. So we go to different applications of these proof systems, so real-world applications, and discuss a bit the trade-offs made here and how they look and what they how they perform. So the first, the pioneer, so to say, was the Zcash in October 2016, and it used this cross-16 Zk snark, and the purpose was a just minimized payment system like Bitcoin. It was actually based on a fork of Bitcoin, but then introduced these Zk snarks, proof of work, and the UTXO model, but allowing private transactions. And this system still works today. But the transactions are not yet so fast because, it's an older system already, 2016, and much of the improvements of the last 3-4 years could not yet be introduced in the Zcash system. The next is also a privacy application. It's called Aztec. This is a system based on the Ethereum blockchain. And the purpose is, it's called a privacy engine for Ethereum, enabling to hide the value of transaction over the Ethereum public mainnet. So, for example, for enterprise applications, so nobody can see how much value I transmit over the blockchain, but it does not conceal the sender and receiver of the transaction. And this shows an interesting aspect of zero-knowledge proofs, an interesting property, because we have so-called selective privacy. I can disclose some parts of the transaction. Here, for example, the sender and receiver. And this is, for example, in particular interesting for law enforcement organizations, that they can, for example, blacklist addresses where they assume illicit activities like drug trade or something like that. Therefore, in this system, still visible the sender and receiver of a transaction. So the law enforcement authorities can check whether anything wrong is done. But on the other hand, the value of these transactions is hidden. That, for example, competitors cannot look how much value is transferred with this transaction. A similar application is quite new. It came into existence only in April 2020. Also on Ethereum is a so-called mixing service, which provides non-custodial anonymity of ETH and ERC20 transactions on Ethereum. Non-custodial means you not have to place your funds, your coins in the hands of someone else, for example, an exchange, but can keep it in. You can keep the possession of the private key and still make the transaction. Here it's different to the Aztec system. Also, you do not reveal the source of the funds. So not only the value is private, but also the source of the fund is private. What, for example, law enforcement may find not so good in some instances. Another application, as said, and the most important one, in my view, are the so-called CK rollups. And the first one, which went live, I think it's a so-called CK Sync, starting to June 2020. It's called a layer 2 scaling solution because it's on top of the Ethereum mainnet. It's not part of the mainnet, but it's on top of the mainnet, increasing the transaction throughput of the Ethereum blockchains. So here another system is used called Plonk for batch verification of several thousand transactions, gradually enable throughput of 2,000 transactions per second. Privacy can be enabled at a later stage. Also here, we have the selective privacy, but it's quite astonishing. We have 2,000 transactions per second, so that's 100x of what the Ethereum blockchain itself can handle, even with a quite recent increase of the gas limit. That's how CK rollups work, and we have two further applications of rollups. One is loopring, which is also quite interesting. Here we have two parts: a cryptocurrency exchange working with from March 2020, and the payment solution is also from June 2020. So here we can perform trades between ERC20 tokens, and they enable, with using CK snarks, could not find out which ones they use, but also 2,500 trades per second, decentralized trades. So this is also part of the so-called decentralized finance DeFi ecosystem. User balances are stored in Merkle trees, and we have also the loopring payment system provides free of charge. So the gas costs which are required are paid by loopring itself. Instant ETH and ERC20 payment solution with up to 5,000 transactions per second. So this is a number which is, for example, performed by PayPal. One caveat, but is present because all transfers happen on the loopring CK rollup. So the sender of the money and the receiver of the money, both their addresses have to be within this rollup. Otherwise, the proof cannot work. Users must be on the CK rollup to send or receive payments. Therefore, they have to register an account, making an initializing on-chain transaction that ties an Ethereum address to one slot in the CK rollup. So you have to make one initializing traditional transaction with the associated cost, and when you are there, you can make this free of charge token transfers using the CK rollup. But of course, both sender and receiver have to make this initial transaction, and therefore this makes adoption of these systems a bit more difficult because, both parties have first to become, so to say, members or establish links to these CK rollup. And a second very similar application is Diversify. They have also cryptocurrency, non-custodial, decentralized cryptocurrency exchange. They use a different proof. They use these CK stars, and they can handle, as they claim at least, up to 9,000 private high-speed exchange transactions per second. So these are designed for high-speed traders, for real speculators. Then we have another application, this time not on the Ethereum blockchain, but it's a blockchain of its own. But this is still in test phase. This is not yet in mainnet status. So the purpose is a lightweight proof of stake cryptocurrency blockchain network having constant block size. And this CODA protocol stores on the blockchain recursive CK snarks, so we can snark of snark of snark of state transitions instead of transactions and signatures itself, in order to reduce the block size to 25 kilobytes. So here we use the CK proofs at the beginning for the whole blockchain, not only to batch some transaction and then put it into the blocks. The whole block is composed of one proof, therefore it's so small, 25 kilobytes, and these are recursive snarks, so you can update it by generating a proof of the proof and so on. It sounds maybe a bit too good to be true, but if it shows whether this really works, it's still on testnet state. There's one further, I think, interesting application, the so-called baseline protocol. Maybe you have heard about this already, because here are really the big industrial players involved. We have a cooperation of the accounting firm Ernst & Young, EY, Microsoft, and Consensus. And the purpose is to produce an open source protocol on top of the Ethereum blockchain, enabling confidential and trust minimized collaboration between enterprise software. So, for example, SAP, so that the SAP systems of different companies can collaborate with each other. So they can talk to each other without requiring email or fax systems, and then put it again in their respective enterprise systems. So it's a very ambitious project, and they have also many partners shown already trying this out, and they also use zero knowledge proof, again cross 16, embedded in Ethereum smart contracts, which are used for confidentiality as well as scalability. So they are quite optimistic about their system. But it's still under development. Of course, this needs to be integrated with systems. But in my view, a very interesting development. And the last application I will talk about here is called Findora. It's also testnet. We have a German guy here from Hamburg, which is one of the co-founders. This is also a public blockchain network for encrypted transfer and verification of financial assets. So this is in the financial world. So if I have, for example, securities and want to transfer them and verify the transfer and make settlement and all this, is a blockchain of its own, not based on the Ethereum blockchain. And here, supersonic CK snarks are used for confidential data verification, for example, for settlement of a transfer of, for example, company shares or other securities from one party of the other, but also still intestinate. Are there any questions at this point with respect to the applications?
So there are some questions about the applicability, but also we have to keep the eye on the watch, because we only have 5 minutes left. So I have to be a little bit selective there.
Okay. But we are almost through, yes.
Okay. By introducing encrypted transactions, aren't we violating the transparency aspect of the blockchain? Also, how would so maybe we start with the first one. So, are we violating the transparency aspect of the blockchain by using encrypted transactions?
Yes, of course, we violate if it's encrypted, is no longer fully transparent. And therefore, we have this selective transparency or selective privacy. So parts of it can be private, parts of it may be transparent. But for example, as I said, for business application, most companies would not and could not participate if everything, including the values of the transactions, would be transparent.
Yeah. Also, to add a little bit on from the lecture side, I think transparency is always a property in terms of, okay, can I verify what's going on in the blockchain? And in terms of, okay, if we think about private blockchains, there is no verifiability anymore. We don't see anything, but the transparency requirement for myself is still fulfilled if we can verify the contents of it, even if we cannot see the exact amounts that are transferred. Okay, so next question. So how would illicit activities be detected, since we would be unable to see uses like extremely high gas price for seemingly normal transactions?
For example, there is, for detecting illicit activities, exists already a lot of analytic tools, and the authorities already have quite good knowledge, as far as I know this, to which pattern are typical for illicit activity, and then they can block particular addresses where they see this illicit activity, and then block these addresses that nobody can transfer funds to these addresses, for example.
Yeah. Okay. Thank you. I think there's a question that applies to many of the protocols based on Ethereum, and I'll try to get them together in one question. Mm-hmm. So when we talk about smart contracts on Ethereum and we include somehow anonymous transactions in there, or we can remove sender, receiver value, something like that, does the blockchain interaction, because accounts still have to call the smart contract, accounts deposit ether, they withdraw ether, so does these operations basically lead to losses of privacy, so to say? Or should they always, if they say, okay, I only want anonymous transactions, I should stay within the smart contract?
I think it's an improvement of privacy with respect to the current situation. I think that presently each smart contract is transparent, so you can look into the smart contract and see what's happening there. So every use of these zero knowledge proofs, which would rather increase privacy and reduce transparency.
Okay. We covered that one. So why is Loopring Pay free of charge? How do they handle spam transactions?
They are momentarily free of charge because they pay the gas fee for the the whole batch transaction. So for each transaction, the fees would be very low, lower than 1 cent. And as a marketing action, they pay it themselves because it's so small, the fees. So for the users, it's free of charge. But from the viewpoint of the Ethereum network, the fees are the same, but they are much lower because they are batched.
Okay. So I think we are right now out of time. I think we can do a little bit of overtime to finish the slides here. And
okay, yeah, I think I'm just maybe 2 or 3 minutes. So I want to touch on the verifiable delay functions, which is an interesting concept. There, this Hamburg guy Benedikt Bünz was also involved here. This is very new, also from June 2018. This is a function that takes a prescribed minimum time to compute. This is a bit like a proof of work, but non-parallelizable. Using, for example, recursive hash functions, so hash function of hash function of hash functions, and you can show with this verified delay function that the input value you put into it has a certain age, so is a certain minimum time old. In particular, this would work well if, and this is also planned, if a dedicated hardware, for example, an ASIC, is also provided open source, so everyone can use for this verifiable delay function, use this optimized hardware, calculate this verified delay function, so everybody is on the same page, has the most efficient hardware, and can show that the original value has a certain age. This can be very useful to prevent fraud or front-running on exchanges, online auctions, to prevent, for example, last-second cheating, also games prediction markets. And the last one I want to discuss is the so-called aggregatable subvector commitments for stateless cryptocurrencies. So just the concept of stateless cryptocurrencies, this is a paper published very recently. The authors include Vitalik Buterin, Justin Drake, and others from Ethereum Foundation. Therefore, yeah, maybe something like this is Ethereum 3.0 in 10 or 20 years. A stateless cryptocurrency or stateless blockchain neither miners nor cryptocurrencies uses to store the full blockchain. Instead, the blockchain state consists of users' accounts, balances is authenticated using commitments, so these proofs. Miners only store a succinct digest of the blockchain state. Miners validate user transactions, including proof that they have sufficient balance, so they show that they really have the money. And the interesting point, users synchronize or update their proofs as new blocks get published. And this is the important point. In this paper, they have found scalable and updatable proofs. So the proofs no longer have to be calculated new with every new block generated. The proofs can simply be updated. And that's the new feature of this particular commitments, and this would be, of course, also a very useful functionality for future blockchain scaling, but this is still very much in the future. I think that was it from my side, and thank you very much for attention and interest in this topic of zero-knowledge proofs.
Yeah, Alexander or Dr. Esslinger, thank you very much. I think it's a very nice final talk for our lecture, because it really shows the typical properties of computer science. Yeah, there's an innovation, blockchain, which more or less makes computations and transactions, let's say, a core data structure, yeah, the blockchain. And now existing ideas of the past, which sounded at that time maybe crazy, now become more or less an additional add-on. Yeah? It sparks new innovations to solve now very practical problems of privacy and trust. And I think that was, very helpful for me also, that you more or less focused also on the big picture and the dependencies of these ideas without getting lost in the details. Yeah, so that we more or less are now very much motivated to more or less follow more closely what's going on there, and also dig deeper for those which have time and energy to do so. So again, thank you very much, and I do hope the students also got some ideas where this is leading and why this is relevant.